Okay, we are at 2112, the spectrum of electromagnetic waves. Let's bring up the PowerPoint. Now you can see that the frequencies, they start here at 10 to the 3 and go up to 10 to the 22 with a little tiny color band right in the middle. That's our visible light. So there's a whole bunch of um, different bands that we use, and there's a whole bunch of different wavelengths that we use. Uh, Not shown here. There's some VLF, very long, very low frequency uh, antennas and radio signals used for navigation. They also use, because of these long wavelength antennas, long wavelength signals that can penetrate water very easily. They're used for submarine communication. Some people want the military to stop using them because of they disrupt. Some people feel that they disrupt whale communication, and just uh, the waves hitting the whales. They don't think it's good for them. It's I'm not making a political statement or anything. I'm just saying what some people believe. But you have very low frequency um, waves from 3 kilohertz, 3 hertz to 30 kilohertz, and the wavelengths are 100 kilometers to 10 kilometers. You'll notice that the as the frequencies get larger, the wavelengths get smaller. So when you go much lower in frequency, your wavelengths get much larger. So you can see the visible in the top green box. The visible light spectrum is expanded to show details of the colors. We typically measure the wavelengths in nanometers. 400 nanometers being violet, 700 nanometers being red, and everything in between, green, violet, blue, green, yellow, orange, red. Um, they range from 400 nanometers to 700 nanometers. You can get into the infrared, which is in the um, thousands of nanometers, and into the ultraviolet. There's ultraviolet A, B, and C. Those are, like 200 nanometers to 380 nanometers. I'm just going off of memory. I may not have the exact numbers correct. We did some work on, or at least some proposals on underwater communications using uh, some of these ultraviolet signals. Um, anyway, so this is the spectrum. We'll go through it little by little. And then now remember, the speed of light, c, is equal to the frequency times the wavelength, lambda. So if you take the speed of light divided by the frequency, you'll get the wavelength of the wave that you're looking at. Uh, so let's continue on. And we have some common uh, terms here. A micrometer is 10 to the minus 6 meters. What would that micrometers is just below visible light. You see, there's 1 micrometer. So you're uh, in the infrared area, but typically we use thousands. I'm used to using thousands of nanometers instead of using micrometers, but it's not micrometer. The micrometer is a little tool you use for measuring. This is micrometers. Nanometers is what we use for describing light wavelengths. And then there's angstrom. 1 angstrom equals 10 to the minus 10th meters. And some people still use that. It's a very common uh, unit. You'll see it used in astronomy and stuff. I tend to like nanometers. I did a lot with light spectrum, and so I'm familiar with nanometers. I did a lot of the laser work, and So I'm familiar with nanometers. Okay, so here we have just um, the TV, AM. You know, the WOEI is 1200 kilohertz. That's 1.2 megahertz. But the AM radio uh, is in the kilohertz range. Then you go to TV and FM. I listen to NPR a lot. That's what is that, 89.1 megahertz, and a lot of your TV is uh, in that range. We're looking at the square box down at the bottom. Microwaves, um, I don't really know why they're microwaves yet when the micrometers is still quite a bit up the chart, but they call it microwaves. Then we get into the infrared, just below the visible light. Let's see, am I missing anything? No, microwaves have wavelengths ranging between 1 millimeter and 30. Oops, I'm going in the wrong direction. Microwaves have wavelengths ranging between about 1 millimeter and 30 centimeters, and they're generated by electronic devices. Uh, then we get into the infrared. Some people call them heat waves. They're it says incorrectly, but they're produced by hot objects uh, and molecules, and they have wavelengths ranging from 1 millimeter to the longest wavelength of visible light is 7 times 10 to the minus 7 meters, which I would call 700 nanometers. Um, the they are really readily absorbed by most materials, and that's why things get warm when exposed to infrared light. Then we have the visible light spectrum. Again, I here the book talks about 10 to the red being 7 times 10 to the minus 7 meters, and the 5.6 times 10 to the 7. I like 700 nanometers, 560 nanometers for the yellow green, and 400 nanometers for violet. Um, then you have the ultraviolet. Uh, these range, you get ultraviolet rays from the sun, um, 400 nanometers down to zero point 0.6 nanometers. It's an important source of ultraviolet light. Most glass blocks a lot of the ultraviolet light, and you have specialty glasses to knock out the UVA, UVB rays. Um, most of the uh, most of the ultraviolet light from the sun is absorbed by atoms in the upper atmosphere or stratosphere. Um, because it's fortunate because UV light in large quantities is harmful effects on humans. Um, so let's see, wrong way. X-rays. X-rays are electromagnetic waves with wavelengths from about 10 nanometers down to 10 to the fourth nanometers. The most common source is X-rays of the acceleration of high-energy electrons bombarding metal targets. And they penetrate. They're easy to damage or destroy living tissues. So that's why most X-ray operators have a dosimeter that measures how much they've received, and you're only allowed to receive so many REMs, Röntgen equivalent man, for over a period of time. Gamma rays. Gamma rays are electromagnetic waves emitted by radioactive nuclei. They have wavelengths 10 to the minus 10 meters to less than 10 to the minus 14 meters. They're highly penetrative and can cause serious damage when absorbed by living tissues. Um, Okay, let's see. Now the spectrum of electromagnetic waves. Here is a the Crab Nebula observed by uh, number by A is an X-ray image, B is an optical image, C is an infrared image, and D is a radio image. And you can see that it gives different images for the different spectra. Um, they use these different regions of the electromagnetic spectrum to see the various features. Um, so, and I think that about does it for the spectrum of electromagnetic waves. And we're going to finish off with a very short section on the Doppler effect of electromagnetic waves. We covered the Doppler effect when we studied sound at the beginning of this summer session. We're going to revisit it. It's a little simpler, and we'll just explain why.